So now let's find the point probabilities of the zero modified version of M. So what we want to do is to find the point probability, so the probability that n is equal to some value, for that value being 0 or 1 or 2 and so on and so on. So already now you've probably understood that the case where n is equal to 0 is kind of special. That's kind of the whole point of talking about a zero inflated version of M, a zero modified version of M, which means also that the case for n equal to 0 should probably be handled separately. So we will split up into two cases. Case 1 is the case where n is equal to 1, or 2 or 3 and so on, and then case 2 where n is equal to 0. So let's take a look at case 1. N greater than 0. So assume that n is equal to 1 or 2 or 3 and so on. Then what is the probability that our stochastic variable n takes that value? Well, first of all, n is only equal to a non-negative value if is only equal to a strictly positive value if I is equal to 1. Also, we need m. So in the case that I is equal to 1, then n is equal to n if m takes the value n, right? Because if m takes the value n minus 2, then n would be n minus 2. So what we have here inside this parenthesis is the exact equivalent of what we have inside this parenthesis. Normally, we say that two events are equal if they include each other. Or if they're equivalent. So n equals n if and only if I is equal to 1 and m is equal to n. Hence, these two events here have the same probability because they describe exactly the same thing. Now what can I do? Well, I can use the fact that I and m are independent, right? We have assumed that I and m are independent. So I is independent from m. Hence, we can split this up into the product of probabilities. And the exact rule that we use here is that if I have two independent events, then the probability of their intersection is equal to the product of each of the probabilities. So if A and B are independent, then this happens, right? So hence I can split this up as the product of the probability of I being equal to 1 and the probability of m being equal to n. And this is then equal to P, so the probability of I being equal to 1 is P, then multiplied by the point probability for m and n, which is Pn. So what I have used here is just independence. However, what if I and m were not independent? Well, in that case, you could have used the calculation that the probability of a joint event is equal to the probability of a conditioned event multiplied by the probability of whatever you condition on. So this just follows directly from the definition of conditional probabilities. And in our case, since I and m are in fact independent, we can just say that the probability of I being something given M is just equal to the probability of I being that something, because the extra knowledge of M does not contribute to changing this probability since I and M are independent. The reason why I just bring this up is not because that we're actually going to use it in this exercise, but that you might encounter exercises where I and M are not independent, in which case you will need the definition of conditional probabilities. Okay, so now we have found the probability that n is equal to n for the cases where this n is greater than 0. So this is in part the answer here. Now we take a look at the other case where n is equal to 0. So case 2, n equals 0. Then the probability that n is equal to 0 can be split up as such. Again, we consider the variables that define n. What should those variables be for n to be equal to 0? Well, n is equal to 0 if and only if I is equal to 0, or m is equal to 0, right? So if I is equal to 1 and m is equal to 0, then n would be equal to 0. If I is equal to 0 and m is greater than 0, then n would be 0. If both are 0, then n would also be 0. So I can actually split this up into 3 cases. So the first case is I is equal to 0 and m is greater than 0. So that's the first case. The other case is that I is equal to 1 and m is equal to 0. And the third case is that I is equal to 0 and m is equal to 0. I mean, you can do this exercise a lot of different ways, but this is just really a really basic way of doing it. Because now what I've done is I've split this up into 3 disjoint cases. So I can just take this as the probability of I equals 0 and m greater than 0, plus the probability that I is equal to 1 and m is equal to 0, plus the probability that I is equal to 0 and m is equal to 0. And that is just equal to the probability that I is equal to 0 multiplied by m greater than the probability that m is greater than 0. So this follows by independence, right? So I can split each of these joint probabilities up using independence of m and I. And what I get is 1 minus p multiplied by the probability that m is greater than 0, which would be 1 minus p0, right? And then actually here I have plus 1 minus p multiplied by the probability that m is 0, which is p0. So these two kind of just add up to 1. So that was kind of superfluous. I could have just removed this and then written greater than equal to 0. And that would just be I is equal to 0 and m is anything. Anyways, then I also have plus the probability that I is equal to 1, which is p, multiplied by the probability that m is equal to 0, which is p0. And this gives me 1 minus p plus p multiplied by p0. So in the case where n is equal to 0, the probability that n is equal to 0. So the probability that n is equal to 0 is given by this, whereas the probability that n is equal to some other value than 0 is given by this. So if we want to sum this up, then the way we could do it is to say, well, the probability that n is equal to some value n, so for n going from 0, 1, 2, and so on, then the probability that n is equal to some value n is given by p multiplied by pn. So this covers all the cases where n is equal 1, 2, 3, and so on. And in the case where n is equal to 0, then we also have this, so p multiplied by p0, but also we will have 1 minus p multiplied by the indicator that n is equal to 0. So in the case where n is equal to 0, we'll also add on n minus p. So I would mean that this would be the final answer that I would give in such an exercise. So see the next exercise for the proof of the over dispersion. See you guys.